in this talk, you know, it's the very kind of breezy, high-level discussion of joint SDMs, which has been this massive and growing literature over the last 10 or 15 years. I'll point out that there's many kind of existing operational versions, and I don't think that the book is closed on what is the best to use in what context at all, you know. So, you know, one of them is this HMSC that Otso Ovoskainen and colleagues in Finland have been developing for almost a decade, as far as I can tell. You know, Jim Clark and colleagues have the generalized joint attribute model, or its extension to include time, GJM time. I've been working on VAST that sort of rolled up a bunch of different sort of research models I've been developing up until then. And there's this finite mixture of regression models, FMR, that folk at CSIRO have been developing over a decade. And this is just a scattering. I mean, Otso has a paper contrasting a bunch of these and lists, you know, 20 or 30. These are sort of some of them that I think are under active development and have sort of a large user base and interface. And I'm not going to try to compare VAST with all of them, but instead I'm just going to point out, I mean, VAST, you know, one person has described, you know, back to me that VAST is sort of set up as like a Swiss Army knife. And so you can take our package VAST and you can use it to fit a spatial factor analysis model, which is typically a kind of small model. You could fit a multivariate index standardization model that's kind of medium size over time and includes temporal variation. You could fit an empirical orthogonal function analysis, or EOF analysis, and that's the third section. There's a spatial dynamic factor analysis, or kind of dual ordination, some ordinating across time and species. There's what I've been calling a spatial mice model. You know, in the fisheries literature, we talk about models of intermediate complexity for ecosystems that has vector interactions, and I'm not going to talk about it much, but that's vector autoregressive spatiotemporal models were kind of separately developed by a bunch of people in ecology, I don't know, 5 years ago, including VAST. And then there's this kind of hodgepodge of joint demographic models, you know, ways of looking again at condition or length or energy density, stomach content, these sort of rates measurements in a joint model with density. In some ways, it kind of resembles to me like the kind of Carey Schaub sort of integrated population modeling literature. And like them, I don't, you know, sort of a growth topic. So to remind people, these, you know, the spatial variable is estimated, this omega term is a matrix that has rows for every knot. And then it has columns for one or more factors. And so if you have a univariate model, you can have 0 factors or you can have 1 factor. You can't have more than the number of categories in the particular structure that I'm using. But if you had 10 species, you could have anywhere from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 factors. And so, you know, just as an example, I'm showing here kind of how to think about this in a case that you have 3 species or 3 categories. And there's specifically this topic of rotation matrices that comes up. So this is confusingly written a little bit, but if you had 3 species, you could have a full rank loadings matrix L that's a lower diagonal matrix, which means it has zeros on the upper diagonal. And so if you have 3 species and it's full rank, you have this lower triangle matrix with 6 elements to estimate. Instead, you might have 2 factors, in which case you've only got 5 coefficients instead of 6. Or if you only have 1 factor, you've only got 3 coefficients to estimate instead of 6. And a property of this model is that the covariance among categories for a given location, this is sort of shitty notation, is is this loadings matrix times its transpose. So if you've got 3 species, you've got a 3 by 3 covariance matrix that it's trying to estimate, and that is generated when you estimate these loadings matrices. So the loadings matrices are what generate the covariance among species, and then you've got these sort of reduced rank orthogonal axes of variation that I call factors, based on similar terminology in factor analysis, like the multivariate technique, or dynamic factor analysis that Alan Jure has developed 15 years ago or so. Introduced to ecology, I mean. So the key though is that this loadings matrix has this set of zeros in the upper diagonal, and so it's not itself that interpretable. Instead, I typically, and VAST does this automatically by default, it rotates that loadings matrix using a rotation matrix that I'm calling H here. And it rotates the L matrix by H, and it rotates the factors by the inverse of H. It's a rotation matrix, since that's the same as the transpose. And so if you do the algebra, that doesn't affect the covariance at all, and it actually doesn't affect the predictions at all. It's the exact same model. It's just a different way of visualizing the axes of variation. And so similar to factor analysis, there's a Varimax rotation. There's what I call a PCA rotation, which for some reason I don't know what it's called in the factor modeling literature, but it makes a lot of sense to explore. The PCA Varimax is designed to optimally discriminate among groups. So coming up with a loadings matrix that has a high value for some species and a low value for others. The PCA style is instead defined to visualize dominant modes of variability. And then there's sort of a literature about oblique rotations that I've never particularly bothered with. The same thing occurs for spatiotemporal models, where you've got 2 different loadings matrices that correlate across time, correlation among correlation across species and years, and orthogonal factors. And so, in 3 minutes or so, we're going to pick up an example of doing a spatial factor model. And I first kind of, documented this, for 16 rockfishes off the West Coast. But I will just quickly breeze through and we could come back to it. I mean, with a multivariate model, you can also do this for size or age classes and do expansion of size and age comps based on sampling. So again, like if you want to generate inputs for stock synthesis, you can use VAST to make an index abundance and also make comps based on, spatially unbalanced or some other design of age or length subsampling. You can do these same things to do what's called EOF, and we'll talk more about that in detail. You can do spatial dynamic factor models and look at their evolution over time, shown as rows in this panel figure. And joint SDMs that generate a bunch of covariance matrices, or even these sort of mice in space models where you can estimate sort of a B0, you can estimate reference points, sort of similar to what stock synthesis does. So, again, this kind of Swiss Army knife philosophy is, shared with stock synthesis, where, like Rick, I would say that I think that we'll always need a community of people building custom tools, but there's other times when you need sort of a single kind of operational code base that's been reviewed, that has a large community of users that can do a bunch of different things, and that's sort of what VAST has been trying to do for marine systems. So, just to close the loop on this Dharma thing, I think this is the thing where I saved all of the plotting output out, and so I'm not totally sure if this will work, but Dharma works the way it should. You just take the object and do a plot call on it, and then curious if they have a better documentation here. Anyway, so yes, I mean, this is too complicated for me to do on the fly, but it looks like, you know, there's different ways I could modify those plots, the quantile diagnostics from Dharma, and plot them. And that's saved as an output from that index standardization model. So, okay, so I'll put that out of my head because I don't want to get too caught up in details. Does anybody have any questions before we kind of switch over to the code for a spatial factor model? Okay. Yeah, I'm sorry, Jacob, in this case, that you are the person who's on my screen. I don't know if I was screen sharing your face, staring at everybody. I don't know exactly how it decides who's on the screen for me, but
it's just the last person who spoke.
And Cheryl, you're muted.
It picks the prettiest among us.
I'm sure, exactly. I'm sure. Great. So yeah, I'll switch over to the spatial factor model, and I'm just going to do kind of the same thing. I mean, I'm just going to I actually ran one where I modified it. I'll just make a new thing called on the fly. I don't know how useful this is really, but so anyway, I mean, the point is that I'm just trying to save the output to some place so that you can see what I'm actually running on the fly here. It's not strictly necessary to do it this way. So I'll just kind of walk through the same input and try to show why it's different. Let's see. There we go. So zoomed in, and then I'll set that direction, you know, I'll point at that empty directory when I start this out. And in this case, I'm loading a different example called 5 species ordination. And this is just a different, you know, data set that I pulled off somewhere, I mean, off the Alaska Center. So, you know, there's a plot called sampling data again. Sorry, example. So in this case, there's a category called, or a column named species number 1, 2, 3, 4, 5. You know, years 1983 to 2015, catch, area swept, lat long. So kind of the minimum, you know, amount of information conceptually for a spatial temporal model. And in this case, I'm just going to pull the kind of default settings for something I called ordination. I mean, so make settings, you know, the code's online and it has a little description here. I mean, if I type question make settings, I can see that ordination is a multivariate ordination to identify similar species. So this is just kind of settings for ordinating. And in this case, what's different is this plot factors. So field config is 2, 2, 2, 2. So it's estimating it's estimating 2 factors explaining the dynamics of 5 species with respect to the spatial term omega, the spatial temporal term epsilon, and the temporal main effect beta for each of the 2 linear predictors. And so there would end up being 6 covariance matrices, and that just seems too much to usefully walk through to, you know, in this sort of short time. And so here I then go in and modify those default settings. So looking at it again, now there's 0 for the epsilon term, meaning there's no spatial temporal component. The betas IID means that the betas are being not having a factor model, but just a separate temporal term for every category and every year. And then still kind of 2 factors for the spatial term for each component. And stripping out, if you look it up, stripping out an autocorrelation term that was being estimated in the temporal effect and the spatial temporal effect. So I'm just basically stripping the model back to make it simpler. I'm running sort of the same inputs here, except CI is now a integer that runs from 0 to 4. So it's kind of using C++ counting convention. It starts at 0. And I'm turning off any Newton steps, which are slow, and I'm not getting the standard deviation, which is also slow. And I'll just start this running on my machine, and then I'll toggle over to where I've already run it. So that, you know, the output will look the same. It's gonna yeah, it's not reducing the extrapolation grid in this case because of some difference in settings, which don't really matter for our purposes. And then it's reducing the it's finding out where to put 100 knots, which it did quickly, and then it'll keep doing other stuff. We don't need to look at it. So the output, if you run that whole thing later, kind of cooking show style, let's see. Oh, it's hard when changing the resolution. My R terminal doesn't like. Here we go. So the output, if I run it, I've got an object fit in memory, and I run these results. And I'm just gonna, for the sake of demonstration, just gonna show. Let's see. It's hard. It's even harder to juggle multiple windows when I'm so zoomed in. Here we go. So I'm just gonna show using the core plot package. I'm gonna, if I can find the plotting window. I guess this is an argument for teaching with RStudio. I never bothered to figure out RStudio, so I apologize. So in this case, this is the output from this core plot function that just visualizes the correlations among species. So this is, it's again calculated from this, extracting the loadings matrix L, and then multiplying it by its transpose to get the covariance matrix, converting that covariance to a correlation matrix, and then plotting it with core plot. And I, you know, somebody else could come up with a more attractive way of showing this. But there's 5 species, and it wouldn't take, let's see, maybe I'll just label this. Well, I don't have enough time. So just for the sake of, for this, I won't get too upset. Well, I'll just label it just so it's a little easier to talk about. Names equals that, or so this is going to be silly trying to type.
A names instead of names.
A names, great. Okay. Yeah, like this zoomed in and screen sharing where I can't even see what I'm typing is ridiculous, but yeah, so now it's labeled with the species. So in this case, the spatial niche of pollock and cod with this 2-factor model is estimated to be close to 0. Pollock and arrowtooth have a correlated distribution, and pollock and snow crab have a correlated distribution according to this 2-factor model, and pollock and yellowfin are negatively correlated, for instance. And so you can see that in the output, where looking through this kind of standard output, there's this anisotropy, this distance at 10% correlation that I'm not really talking about in any detail, the extrapolation grid and knots, same data. This is using a PCA rotation, and so the first factor explains 71% of explained variance and is a positively associated with arrowtooth and snow crab. So I'm assuming that's why Arrowtooth and snow crab are positively correlated because they share a dependence on that first factor. They're negatively correlated in the second, which is why they're not more correlated overall. And that omega-1, for instance, is Arrowtooth and snow crab. And then that first factor looks like this. And so both Arrowtooth and snow crab are positively associated with this elevated densities in the middle domain, including the northern portion. And then the factor 2 for omega-1 is negative in the north, which has a positive loading with pollock and cod. So pollock and cod avoid that northern portion, which is shown here. So anyway, I mean, by crosswalking between these loadings, matrices, after rotation, and the maps, you can, you know, kind of visualize what's happening. And then these are the resulting density maps. So there's no temporal effect. There's a temporal main effect, but no spatiotemporal effect. And so there's nothing really to cause the distribution to change. The spatial configuration can't change over time. It can change in the main effect can change. And so in this case, cod, I guess, had higher abundance in 2002 than 2008, shown by the darker colors in 2008. But this is sort of the densities that it generates. And I guess I just want to get to pollock. So this is sort of the same, you know, this is the same data set essentially as what we were fitting in the index model. And so I'm just going to pull over to the index results that we were looking at. So for reasons that don't exactly matter, I guess the window size is slightly different between these plots, but you know, you can see that in an index standardization model, it's more flexible. Pollock are actually moving away from the northern Bering Sea in some years, whereas this spatial factor model doesn't have any structure in it that allows the spatial configuration to change. And so that's why, you know, this right-hand side model is more flexible and also fits better. You could also, well, anyway, yeah, I mean, a person could use AIC, but they'd have to set up a different model to make the same data set in both. And I guess the final thing to look at, well, there's the spatial predictions for every species. So this is the omega-1, the first linear predictor spatial term for Arrowtooth, cod, pollock, and so on. And then the same for the second linear predictor. Here's the map of, you know, here's the QQ plot, and here's the map across species. Here you see, because there's you know, there's no change in spatial configuration over time. Here's an example of a bad map of spatial residuals where there's sort of this persistent value near 1, which I guess means the data are well, anyway, I think the model should be over predicting here in 2003, and for instance, under predicting in Bristol Bay on average across species in 2009, for instance. So anyway, the point being that this map of spatial residuals for the JSDM will probably look worse than the index model spatial residuals. It's not a very fair comparison because this is looking across 5 species and this is not, but yeah, anyway. Yeah, so that's the sort of quick tour of a spatial factor analysis model in VAST. And you know, we've got maybe a minute here, I think, on our schedule for questions, but we can let it slide a little bit if people have a couple.
Dina, go ahead.
Hi, yep. Hi, this is Dina. I had a question. I think I missed when you were describing the when you're showing the pollock from the index model and then compared it to the multi-species model. You said one was more flexible and had a better fit. And I missed which one that was. So I was hoping if you
Yeah.
could explain that again.
Yeah, totally. So that I can actually show, I mean, all of the plots take a little while to run. And so I'll just try to kick this up if I can find so this is the, there's a bunch of optional plots, of course. And so I'm just looking for the index model where I ran it before.
Share your screen.
Okay, yeah, totally, thanks. Screen share. So here's the index model where I ran it before, and I'm still just kind of copy pasting out of this. So I'll get this going. So in this case, I'm going to say plot set. You know, somebody could look up in the docsgen what I'm doing later. But I'm just adding a bunch of extra plots to the output for the index model. And I'm actually not sure what will happen if I try making that full set of plots for the other one too, but I'll just try it. And then we can come back to it in a second. Yeah, 360. So I'm already, some of those are being made. Sorry, everybody's patience is different with on-the-fly coding. Some people, I think, find it helpful to kind of see people actually do this stuff, and others just find it boring. And sorry for the latter. Now I'm generating a common set of additional plots, 3, 16, 17, 6, and 7 for both of these. And just in a different terminal, I'll just call up the document documentation for plot maps. And so 6 is the spatial temporal variation, the first linear predictor. 7 is spatial temporal variation, the second linear predictor. 16 is spatial, the omega 1 and omega 2. And so you know, what I'm going to show, if those run as I expect them to, is that the index model, yeah, right now it's making this epsilon 1 plot. It's taking a second. So the index model, if you go to settings, you see this copy of what it had turned on. And it had turned on this IID structure for epsilon. And so this is the estimate of epsilon 1 that's being estimated as shown in settings. Here's the estimate of epsilon 2. And then it'll also generate, yeah, and then here's omega 1, the spatial term for the first linear predictor and the spatial term for the second linear predictor. By contrast, the JSDM, if you go to settings, it has a 0. I don't know how to zoom in on a notepad by the here. Let's see. Control+. If you go to the settings for the JSDM and look at the field config, it has a 0 for epsilon, which means it turned off the spatiotemporal term. And so you know, it has the omega term that's being estimated, but eventually it'll get to plotting the epsilons, and you'll see that those epsilons are constant across space. They're turned off. And so that's the sense in which the index model is more flexible, is that it's estimating this additional term epsilon that was turned off in the joint SDM. And therefore, that epsilon term is able to estimate a change in the spatial distribution for a given species that the JSDM can't. So,
Got it. Thank you. That's really helpful.
Okay, I'm glad that wasn't too rambly. I was kind of losing myself.
No, but you came around to it, so I was able to hang on.
Great, good, perfect. Yeah, and I mean, again, the key point of Pollock, I mean, if you show a fisherman a map of Pollock, you know, in years with a large cold pool, it's generated by this ice factory at Polinia, south of St. Lawrence Island, that, you know, ice formation cranks out a bunch of brine that sinks the bottom. And so they avoid these cold water in the north. But then in 2008, there was this sort of collapse of Pollock in the middle domain, which is shown up here in these kind of cooler colors. 2008, 9, 10, like Polly wrote a paper saying that we were mismanaging Pollock. But at the same time, the North Pacific Council cut the TAC in half, and it's since rebounded to kind of recolonize that middle domain. So a map, to understand Pollock, you really need to understand the spatial configuration and how it's changed over time. The JSDM doesn't have anything in it that explains that change in spatial configuration over time.